This is a lesson on the first law of thermodynamics in the thermodynamics unit. This lesson pulls some weight. This is a pretty heavy-hitting lecture in regard to fundamental concepts and driving principles. So you're going to see some terminology. You're going to see concept development here at first, which will let us proceed to more calculations with thermal processes in application. So thermodynamics and energy conservation. How is heat accounted for in conservation of energy? We've studied conservation of energy. If you're following me and think about energy in the way I think about energy, I think of it as a state function. There's an initial state. There's some sort of add or loss in between some final state. And this is very much like your checking account each week or month, right? You have some initial state, you have some go in or out, and you have some sort of final state. You don't care how stuff went in and out. You just know that it did overall. And so how we think about that with conservation of energy in thermodynamics is to break up this add or loss into a work done and a heat in or out. And remember, both of these are energy in transit. They are process quantities. So they're not a state of energy. They're energy moving from one state to another. And the big concept here is heat transfer and doing work are methods of transferring energy into or out of the system. Okay, so again, we're looking at energy states and we're accounting for anything that was add or lost, and we can divide it up into two little components. Physicists, you will see, break energy up into many different ways, and I'm going to continue to do that during this lecture. You will see it be broken up in different ways in chemistry, such as Gibbs free energy when you think about enthalpy, as opposed to the way we're going to think about it in physics when we talk about energy and move towards entropy. Okay. So, incorporating heat into energy conservation, we must break down what's going on within the solid. Of course, there's some sort of coherent kinetic energy or potential energy, which is what you've been used to. When we take a macro object and we move it around on the planet and the center of mass does things, that's a coherent energy, and we can measure it in terms of kinetic energy and potential energy. Within that object, there is internal energy, and that's independent of the quantity capable of being stored. So we're going to have incoherent kinetic energy, which we think of as 3/2 kT for a gas, right? So that's incoherent. The center of mass is not moving, but each one of the molecules within that substance is moving, and we're going to account that into the internal energy. There are also incoherent forms of potential energy, and I'm bringing up them just so that you are aware of them. We are going to focus on the thermal energy, but remember, incoherent potential energy can be stored in chemical energy. I can burn something. That's incoherent potential energy. There's electrical energy. Each one of those atoms is composed of electrons and protons, right? There's electrical stuff going on. There's atomic energy. I could take it like a bomb and make it blow up and get energy out of that. There's nuclear energy that keeps the little molecules in the nucleus of the atom together. So that's nuclear energy. And that to me is akin to Einstein's E = mc squared. So we know there's lots of energy in just you sitting there. Just you sitting there has so much energy. We're looking at only specific components of that energy measured in specific ways. So let's look more particularly at energy. We know this is true. The initial energy state plus any work on the system plus any heat into or out of the system equals the final energy state. And I'm going to divide that energy state, the initial and final energy state, into some components. We have the coherent mechanical energy and then the internal energy. So I took this term and put it in here for the initial energy state and the final energy state. Okay. What we care about is energy changes. And when I think about this equation, I just move EI to the other side, the initial energy over to the other side, I get the change in energy, the difference in energy from final to initial will equal these energies in transit. Whatever I measure to begin with, I subtract it from whatever energy state to end with, and the difference there had to be any energy in or out of the system via heat or work. Okay, we're going to look at this EF and EI closer. If the container of molecules is not changing coherent energy, so we're going to lose these two terms and these two terms, we're going to see that we have a U final minus U initial on this side still, and Q plus work on the next. And then you will see that's where we get the first law of thermodynamics. It is conservation of energy in a very specific form, considering specific energies. The first law says the change in internal energy of a system equals the net heat transfer into the system minus the work done by the system. Okay, so there was a little bit different form on the prior slide, and you may have noticed it, and I'll talk about that in a second. So on this side, we have change in internal energy. Remember, we're looking at thermal energy only, so we can quantify that energy as 3/2 kT for a gas times n number of molecules. You'll have an initial temperature, you'll have a final temperature, and you'll be able to find a change in internal energy. Over on the other side, we have the energies in transit. Of course, we have heat, which can be measured as an energy, some sort of joules, and then we have minus work by. On the previous slide, I had plus work on, and you may see this equation in other books. And that's why I'm talking about this now, so you're not confused about why you see different forms. Remember, do you know which Newton's law says these are equal and opposite to one another? Newton's third law says if there's a force on one object from a second object, then the first object exerts a force on the second object. So if there's a force this way, there must have been a force that way. So if this does work on, there's work by the other object. And so that's why there's a minus sign in there, is to say minus work by. This is consistent with many texts that I've referenced, but if you see any differences or they ask what's the work on as opposed to the work by, watch out for that negative sign. I talked about this. Delta U is the change in the internal energy given by kinetic theory. W and Q cause changes only in U. Work and heat cause changes only to the internal energy and thermal energy. We're not looking at coherent energy. We're not looking at chemical. We're not looking at atomic. We're just looking at thermal energy. So that's why we're using only this equation to account for delta U when we consider the first law of thermodynamics. The last thing here says the internal energy U of a system depends only on the state of the system, and again, not how it reached that state. We don't care how the heat got in or how the heat got out. We don't care how the work was done on or by. It doesn't matter. All we care is about the initial state and the final state, and we can do some numbers and figure out those values of work and heat in between. To review the terminology that I've gone over, just so it's straight in your head before we move forward to applying this equation, let's talk about each one of these individually and what they represent conceptually. Work is energy transfer at the macroscopic or coherent level. A force acting over a distance. So again, I reference Newton's laws, still thinking about forces. What is the object doing force? What is the direction of the force? And what is the displacement vector? Most often with thermodynamics, you will see the wall of the container move. That's the easiest way to do work. And that should make sense because we're looking at changes in volume. And if the container wall moves, there's work done and we have a change in volume. So that's the relationship there, and you'll see that more as we move into the next lesson. Heat, Q, is the transfer of thermal energy between surroundings and systems or from one object to another. Does transfer of heat necessarily cause a change in temperature? This is some place in your intuition that you're going to have to adjust, because your intuition always, in our real world, where we experience it, Most often when we think about heat, we think about temperature differences, and that's what causes heat transfer. Remember, there's different ways to transport heat, the different mechanisms. So often there is a temperature difference. I am going to say, and you can think about this, I'll give a couple of examples, that doesn't always happen with a temperature difference. It can happen isothermally. And remember, that's one of our thermal processes is isothermal. An example of an isothermal, you're like, Sarah, this can't be real. An example of an isothermal process is phase change. Remember, phase changes happen at a constant temperature. Because we're studying gases, we're going to think about temperature differences. But thermodynamics applies to more than just gases. So an isothermal process does happen. It doesn't always correspond to a difference in temperature, but as we study gas, we will see that usually corresponds to a difference in temperature. I'll have an example when we study that in the next lesson, and I'll leave it to that. The last term here, internal energy, is the incoherent chemical, electrical, atomic, nuclear, equals mc squared, all of that, and thermal energy. So we have potential energy and kinetic energy counted in the internal energy. We are only focusing on the thermal for thermodynamics, and it depends on pressure, volume, and temperature. Now that I've established some heavy concepts there, let's just look at a simple basic example in order to apply the first law of thermodynamics. I've written it over here. It says how much heat transfer occurs from a system. Okay, so heat. How much heat transfer? I want to know what the heat is. From a system if its internal energy decreased by 200 joules. Okay, so I see internal energy. I know that's represented by delta U. In the problem, I see that it decreased by 200 joules, so I'm going to put a negative 200 there. It also says while it was doing 50 joules of work, so we're going to say work by equals a plus 50 joules. It was doing work as opposed to work being done on it, okay? So we want to solve for Q. I'm going to rearrange this equation algebraically to solve for Q. Q equals delta U plus the work by. Just move the work by over. I'm going to plug in what I know, negative 200. Work by is a plus 50, and I see that the heat transfer is negative 150 joules. I think this problem is a little sneaky. It says what heat transfer occurs from a system if Q is positive. All right, if this is my system, Q going out of it will be a negative value, right? It's losing heat. This is a heat loss when it's going out of the system. This is a heat loss, okay? As opposed to into the system, if I get Q into the system, that's a positive value. This is heat gain. So I see in this situation how much heat transfer occurs from a system. It's a negative value, so heat is leaving the system. So when you're thinking about energy in transit, remember, ask yourself which direction it is going and whether that corresponds to a positive or negative sign. The second problem I chose is a little bit more involved to show you the inner mechanics of how to deal with a change in internal energy with the temperature involved. The temperature of 3 moles of argon gas is reduced from 540 Kelvin to 350 Kelvin when 555 joules of heat flow into the gas. I'm making note of into. Find the change in the internal energy and the work done by the gas. So it broke this problem into 2 different parts. For part A, we're going to find just the change in the internal energy. For part B, we're going to use all of the first law in order to figure out the work done by the gas. So let's look at part A. Part A asks us to find the change in the internal energy. And I wrote down here kinetic energy. Remember, that's the internal thermal energy that we're looking at, depends on temperature. So let's write down here, U is equal to the kinetic energy, and it will be the total kinetic energy, the number of molecules there, times 3 halves kT. Well, I'm going to note that I'm given moles. which is N. N equals 3 moles. And I can convert this equation to an equivalent form, 3 halves times nRT. This is the universal gas constant. So I can use this equation. And that will take into account all of the thermal energy, all of the internal energy in any state. And I can apply this 2 times, right? I have an initial energy state with an initial temperature. T initial is 540 Kelvin, and there's a final temperature, 350 Kelvin. Okay, seems like we have some pieces put together to write out this equation. Delta U equals 3 halves nR delta T. If I'm finding delta U, all I have to do is find a delta T. N staying the same. This is the universal gas constant. This is a constant value, so I can plug in here delta T. So that equals, plug in some numbers. N is 3, R is 8.314. Delta T, remember delta is T final minus T initial. And in this situation, the initial is higher than the final. So remember to write these in the correct direction, or else you're going to miss your negative sign. So 540, 350 minus 540. We see that the initial temperature is larger than the final temperature. So overall, we're going to get a negative number here. And this turns out to be negative 7,100 joules. And that is the answer for A. We're going to take the kinetic energy of all the molecules, is basically what it is. We have the change in kinetic energy of all of these molecules. And you could use this if you were given the number of molecules, you would use the Boltzmann constant. But since we were given number of moles, we can use the universal gas constant. And that lets us find the change in internal energy. Part B, we're going to apply actually the first law of thermodynamics. It says, what is the work done by the gas? So I'm going to solve this equation for work by. Work by equals Q minus delta U. There's a little bit of algebra here. Move this over here, move that over here. We keep the negative sign. So I'm going to plug in what I know. Q, I know, is, it says when 550 joules of heat flows into the gas. So I'm going to write this out explicitly. Remember, it's flowing into, so that means it's a gain of energy. So we're going to have a plus 5,500. Always think about your sign of the heat coming in or out, or the work being done, whether it's positive or negative, because you can see if you have the wrong sign, you're going to get the wrong answer here. So this is a plus 5,500 minus negative 7,100. So we have minus and negative, so these two will add together in the end, and this is 12,600 joules to 12.6 kilojoules. And that is the answer. This is a positive. Okay, so what we saw is that the temperature of the gas was reduced. It got colder, okay? So heat flowed into the system, which is sort of weird when you think about heat flowing into a system. It usually corresponds to an increase in temperature, okay? So this is where this goes against your intuition. What happened was that heat and the temperature change went into work being done by the gas. So what I'm going to guess, and this isn't information given in the problem, was this gas expanded a lot. There was a lot of work done by the gas. And remember what I said before is that if there's work done, there's movement in the container walls, and that gas is doing work and expanding the container walls. So it got colder, but it also did work.